Welcome to Wildcat Science with Mrs. Haugo. This is physical science and we are in chapter 1, forces. And today we're going to be working on 1.6, friction and weight. So please find your force, motion and energy book. And we are going to be postponing our 1.4 lab about the magnetic force and our 1.5 lab about sliding friction. And so please open up your book to page 13, 1.6, friction and weight. Great, please follow along. So far, you have investigated, or I will tell you, whether the force of friction depends on the kind of surface and the contact area between objects. Well, it depends on the type of surface, and the force of friction does not depend on the area of contact between two objects. What about weight? Does the weight of an object affect the friction for the same surfaces? To study this, we investigated the frictional forces on two blocks of different weights, a shorter, lighter block and a longer, heavier one, seen in figure 1.7. Their weights were 1.3 newtons and 5.05 newtons. Using the procedure from the preceding experiment, we found that the least force needed to move the lighter block was 0.5 newtons. For the heavier block, the least force was 2 newtons. The friction was greater for the heavier block than the lighter one. Okay, when it talks about the procedure from the preceding experiment, they talked about using a block and putting it on a surface and then hooking it up to a spring scale and pulling it with just the minimum amount of force to get it to move at a constant speed, and then reading that amount of force, which right then was 0.5 newtons. And the blocks had different surfaces. This is a rough surface, and different size surfaces, thin, so we will be able to test if the type of surface or the area of the surface, of the contact area, affects friction. And what we will figure out is that it's the type of surface, not the area of the surface, that affects friction. Please take a minute and do a virtual post-it note. Great. We then placed various weights on the lighter block and measured the force of friction for each combination. The results are shown. Before we move on to the next page, let's look at the pictures. So 2 blocks, a short one and a longer, heavier one, each with non-skid material on the surface with the largest area. And then the weights have been added to the short, lighter block. And we're going to look at the data just now. Okay, the data is shown in table 1.3. These data are graphed in figure 1.9. Within the range of the data, the force of friction is proportional to weight. The proportionality constant depends on the two surfaces. It is called the coefficient of friction. So now our proportionality constant that we have been calculating when we're dealing with friction, it is called the coefficient of friction. So same thing, but a different name. So we know the force of friction equals the coefficient of friction times the weight. So data table for the investigation of how the frictional force is related to weight. The total weight is the sum of the weight of the shorter, lighter block and the additional weights that were placed on top of it. So if we look, the short block has a consistent weight, and they kept adding more weights to it, and so our total weight was increasing. And as the total weight of the block increased, what happened to the force of friction? You can see the force of the friction increased. So when weight increases, the force of friction increases. So let's look at the short block. When it's around 5 newtons, as the weight of the long block is up here, so it has about the same force of friction. So it doesn't matter how big it is, it just depends on the weight. Because both weight and friction are forces, their ratio is a pure number if both are measured in the same units. In figure 1.9, both forces are expressed in newtons, hence the coefficient of friction calculated from the graph is a pure number. So let's take a look at that graph, figure 1.9. Okay, so here's our graph, friction versus weight. And a couple questions I have for you. One is looking at the x-axis, total weight in newtons. What is the value of each of these little divisions? Great. Now looking at the force of friction in the y direction, what is the value of each of these little divisions? Okay, great. And now if we look at the total weight of an object as it increases, the force of friction will increase. So we know that there is a proportionality between weight and friction, that they have a relationship. We also know that it is a linear relationship, just like we were studying, and that the slope of this line is the proportionality constant between weight and friction, and which now has a special name, which is the coefficient of friction. So a couple questions for you about the graph. Okay, what is the force of friction if the total weight is 4.4 newtons? So we would go over to 4.4 newtons, we would follow it up to the red line, and then we would go over, and that would be 2 lines over, so 1.5, 1.6, 1.7 newtons. So my question is, what is the force of friction if the total weight is 6 newtons? Great, please do one more digital post-it note for this section. Okay, next up we are going to be taking notes on this section, so please find your binder and open up to your notes section and open up to the table of contents. So please enter 1.6 friction and weight, and then you don't need to start a new page, so skipping 3 lines, whatever page you left off with 1.3 Hooke's law. And then we're going to go to that page in our notebooks, and please skip 3 lines and title it Chapter 1.6 Friction and Weight. So please write this down. Friction increases when weight increases. So like we saw from the graph and from the table, as the weight increased, the friction increased. Also, friction depends on the 2 types of surfaces that are touching. So it will depend on if you have the non-skid surface or the regular wood surface, how much friction there would be when you're trying to pull this block along. So they could have the same amount of weight, but if you have this one down, it's going to take more force to pull it along, so there'll be more friction. And we will find in our experiment 1.4 that friction does not depend on the amount of surface area. So when we're pulling it on this big surface, it's going to have the same amount of friction as the smaller surface. And friction is proportional to weight. As we know, friction increases when the weight increases, so that means that they are proportional. So let's take a look at a graph. I would like you to make this simplified graph in your notebook, please. So this x-axis we're going to label weight, and the y-axis we're going to label friction, and then draw a nice linear line, and that goes as weight increases, friction increases. So the proportionality constant depends on the 2 types of surfaces. So the proportionality constant we know is the slope of this line, and so the slope of this line depends on the 2 types of surfaces. For example, the slope of the line of friction versus weight of the plain wood would be different than the slope of the line of friction versus weight of the non-skid surface. And so our proportionality constant equals our friction divided by our weight. Please write that down. Another name for the proportionality constant is the coefficient of friction. So that is represented by the Greek letter mu, which looks like kind of like a backwards PU type letter. So the proportionality constant is called the coefficient of friction. So the coefficient of friction equals friction divided by the weight. And just like in algebra, we can rearrange this in any way we see fit. So we could say we could solve for the force of friction by timesing weight on each side. It would cancel here, and then we get coefficient of friction times weight. So the force of friction equals your coefficient of friction times the weight. And coefficient of friction is a pure number, which means it has no units. In other words, it is a ratio. Another thing I would like to talk about is mass versus weight. They are not the same thing, although we normally talk about them interchangeably in common terms, but in science they're quite different. So weight is the force of gravity on an object, and it is measured in newtons. And then mass is the amount of matter in an object, and it is measured in kilograms. So for example, the mass of this block is about 150 grams or 0.150 kilograms, whereas the weight of this block is about 1.5 newtons. So the mass is the amount of matter, the amount of molecules in here, the amount of stuff, and then weight is the force of gravity on this object. So they're quite different. So we're going to find our mass in pounds and kilograms, and then our weight in newtons. So please find a calculator or your phone or one on the internet and enter in your mass in pounds. A lot of times we'll call it weight, but that's just in common terms. In science, it would be your mass in pounds. So for example, I have a mass of about 130 pounds. And then to convert that into kilograms, I'm going to divide it by 2.2, and I get 59, roughly 59 kilograms. So I have a mass of 59 kilograms. And now to find my actual weight, I am going to times it by 9.8, and my actual weight is 579 newtons. So there is your mass in pounds, kilograms, and your actual weight. Okay, so which one would change if you went to Mars? So we know that weight is the force of gravity on an object, and we know that acceleration due to gravity changes when you leave Earth. So Mars, Mercury, Moon, Earth, they all have different accelerations of gravity. So which one would change, your mass or your weight? If you said your weight would change if you went to Mars, but your mass would stay constant, you are correct. Good job. Tomorrow we're going to be working on our questions for this section. All right, see you then. Bye.